Namaskar. Today I will discuss the theorems on initial value problem for the nth order. If phi1, phi2, phi3 phi n are n solutions of L of y is equal to 0 on an interval I, they are linearly independent if and only if Wronskians of phi1, phi2 phi n of x is not equal to 0 for all x in I. The proof is entirely similar to the proof of previous theorem. Suppose Wronskians of phi1, phi2 phi n at x is not equal to 0 for all x in I. For all x in I, let c1 c2 cn be constant such that c1 phi1 of x plus c2 phi2 of x plus plus cn phi n of x is equal to 0 for all x in I. By differentiating above equation n minus 1 times, we get a system of linear equations such as phi1 of x, phi2 of x, phi3 of x, phi n of x, phi1 dash of x, phi2 dash of x, phi3 dash of x, phi n dash of x, phi1 double dash of x, phi2 double dash of x, phi3 double dash of x, phi n double dash of x, phi1 raised to n minus 1 of x, phi2 raised to n minus 1 of x, phi3 raised to n minus 1 of x, phi n raised to n minus 1 of x, c1, c2, c3 cn is equal to 0, 0, 0, 0. The coefficient matrix is invertible because the determinant of the coefficient matrix is Wronskians of phi1, phi2, phi3 phi n of x is not equal to 0. On pre-multiplying the inverse of the coefficient matrix, we get c1 is equal to c2 is equal to c3 is equal to cn is equal to 0. This proves that phi1, phi2 phi n are linearly independent. Conversely, assume that phi1, phi2 phi n are linearly independent on I. Suppose there is a point x naught in I such that Wronskians of phi1, phi2 phi n at x naught is equal to 0. Then the system of equations phi1 of x naught, phi2 of x naught, phi3 of x naught phi n of x naught, phi1 dash of x naught, phi2 dash of x naught phi n dash of x naught, and c1 c2 cn is equal to 0, 0, 0. By solutions c1 c2 cn, where at least one of these numbers is not 0, let c1 c2 be such a solution and consider a function psi of x is equal to c1 pi 1 of x plus c2 pi 2 of x plus plus cn pi n of x. Now L of psi is equal to 0. Psi dash of x naught is equal to psi double dash of x naught is equal to dash dash is equal to psi raised to n minus 1 of x naught is equal to 0. Therefore, norm of psi of x naught is equal to 0. But then by theorem, norm of psi of x is equal to 0 for all x in I. Therefore, by definition, norm of psi of x psi of x is equal to 0 for all x in I, but then pi1 pi2 dot pi n are linearly dependent. Thus the suppositions Wronskians of pi1 pi2 dot pi n at x naught is equal to 0 must be false. Therefore Wronskians of pi1 pi2 dot pi n of x is not equal to 0 for all x in I. This is the solutions. Next one, existence theorem. Let a1 a2 a3 dot an be n constants and let x naught be any real number, then there exists a solution phi of L of y is equal to 0 on minus infinity less than x less than infinity, satisfying phi of x naught is equal to alpha 1, phi dash of x naught is equal to alpha 2, phi double dash of x naught is equal to alpha 3 dot phi raised to n minus 1 of x naught is equal to alpha n. Proof. Let phi 1 phi 2 phi 3 dot phi n be any set of linearly independent solutions of L of y is equal to 0 on minus infinity less than x less than infinity. We will show that there exists unique constant c1 c2 dot cn such that pi is equal to c1 pi 1 plus c2 pi 2 plus c3 pi 3 plus dot plus cn pi n is the solutions of L of y is equal to 0, satisfying the condition, initial condition phi raised to I of x naught is equal to alpha I is equal to 1 2 3 dot n. These constants c1 c2 dot cn would have to satisfy phi 1 of x naught, phi 2 of x naught, phi 3 of x naught dot phi n of x naught, phi 1 dash of x naught, phi 2 dash of x naught dot phi n dash of x naught, and so on. c1 c2 dot cn is equal to alpha 1 alpha 2 alpha 3 dot alpha n. Therefore c1 c2 dot cn, the function phi of x is equal to c1 phi 1 of x plus c2 phi 2 of x plus c3 phi 3 of x plus cn phi n of x is equal to phi of x will be the desired solutions. Let phi 1 phi 2 dot phi n be unlinearly independent solutions of L of y is equal to 0 on an interval I if c1 c2 dot cn are any constants. Phi of x is equal to c1 pi 1 of x plus c2 pi 2 of x plus c3 pi 3 of x plus dot plus cn pi n of x is a solution, and every solution may be represented in the form. Proof. Since pi I is equal to 1 2 3 dot n is the solutions of L of y is equal to 0, L of pi I is equal to 0, I is equal to 1 2 3 dot n. Therefore L of pi is equal to c1 L of pi 1 plus c2 L of pi 2 plus c3 L of pi 3 plus dot plus cn L of pi n is equal to 0, and pi is equal to c1 pi 1 plus c2 pi 2 plus dot plus cn pi n is the solutions of L of pi is equal to 0. Let phi be any solutions of L of y is equal to 0 and x naught be in I. Suppose phi of x naught is equal to alpha 1, phi dash of x naught is equal to alpha 2, phi dot phi raised to n minus 1 of x naught is equal to alpha n. By existence theorem, there exists unique constants c1, c2 dot cn. Psi is equal to c1 pi 1 plus c2 pi 2 plus c3 pi 3 plus dot plus cn pi n is the solutions of L of y is equal to 0 on I satisfying psi of x naught is equal to alpha 1 psi dash of x naught is equal to alpha 2 psi double dash of x naught is equal to alpha 3 dot psi raised to n minus 1 of x naught is equal to alpha n. This the uniqueness theorem implies that pi is equal to psi. Thus, pi is equal to c1 pi 1 plus c2 pi 2 plus dot plus cn pi n.